Today I will discuss about a diode clipping circuit where it is said that we need to find out the transfer characteristics. So what is the transfer characteristics? It is that you are varying the input voltage, which is V in, and then you are observing the output voltage, which is my V out. So here there are two diodes whose cut-in voltage is 0.7. So there we need to find out the transfer characteristics of this circuit. Okay, and the next question which I'm going to solve can be easily solved by superposition, can be easily solved by say KCL, applying KVL or KCL, but I found out a different solution, that is using the millmans theorem. Today I'm going to discuss about the millmans theorem, and we will try to solve both the questions say by superposition and by millmans theorem, and let's see that whether we get the equal answers or not. And before solving the clipping circuit question, let's go through the basic. In the top one, what we are doing, we are applying the input voltage to the P part of the PN junction diode, and the N part is connected to the resistor, and we are getting the output. So if my input voltage is greater than say the cut-in voltage of the diode, the output voltage V0 is nothing but V in minus the cut-in voltage that you can observe. Now at the output side, if I add a DC voltage, then what will happen? At the N side there is already a DC voltage added, so my V in has to be greater than VDC plus V gamma, then only my diode can conduct. Okay, so what will be the voltage? My output voltage will be V in minus V gamma. Since if the diode is not conducting, my output voltage will be 0. Okay, so to have a voltage drop across the PN junction from P to N, it has to be V gamma. So if my V in is lesser than minus of V gamma, then what is going to happen? Then only the diode can conduct. So already there is a drop of minus V gamma, so my output voltage will be V in minus V gamma. So now if I add a VDC across it, so when the diode is not conducting, then what will be my output? Then it will be simple VDC. Now if there are two diodes but they are connected in an opposite way, so if my V in is greater than V gamma, then the P to N, which is the input side is connected to P and the output is connected to N, that is get forward biased, and my output is V in minus V gamma. Okay, and when my input is less than minus V gamma, then diode where the P side is connected to the output and the N side is connected to the input, that goes like V in minus V gamma. Okay, so if there is a VDC, then what will happen? When the diodes are not conducting, then my output voltage will be equal to VDC, and when my V in is greater than VDC plus V gamma, then the diode where the P side is connected to the V in and the N side is connected to the VO, that is forward biased. So over there the output voltage will be V in minus V gamma. Okay, when my input V in is greater than VDC plus V gamma, and when my V in is lesser than VDC minus V gamma, then the diode where the N side is connected to the V in and the P side is connected to the output, that diode is forward biased, and then what happens? The output V0 becomes equal to V in plus V gamma. Okay, so here what is my VDC? Here my VDC in the question, here my VDC is equal to 1 voltage. So and my V gamma is equal to 0.7. So what will be the value? The VDC will be 1 and VDC plus V gamma will be equal to 1.7 and VDC minus V gamma will be 0.3. So I hope everyone got the answer. This question was asked in GATE 2023, where it is said that we need to find out the current which is flowing through the 200 ohm resistor, where we can see that there are 3 independent sources. 2 are current sources and 1 is the voltage source. Okay, so if we want to do the superposition, then what we need to do? We have to activate only one source at a single time and then deactivate the other one. Similarly, we have to repeat it for the other one and then for the other one, and then whatever the current which we are getting, that we need to sum up, and then we will get the total current I. But it is time consuming. That I will tell you now, that how it is time consuming. Current capital I1 is flowing from the 2 voltage source, and the current small I is flowing through the 1.2 kilo ohm resistor. Okay, because I'm saying 1.2 kilo ohm because 1K and 200 ohm are in series, that is why. So if small current I1 is flowing through the 1.2 kilo ohm, then the rest of the current means capital I1 minus small I1 is flowing through the 2 kilo ohm resistor. To find out only small I1, we have to do a lot of calculations. Okay, and then we have to repeat it for the another 2 So let's discuss that also. Now we have activated only, say I am talking about the top circuit. Okay, only the 1 milliampere source, and I have kept open the another 1 milliampere source and also shorted the 2 volt source. So there we can see that this 1 milliampere is flowing, and then through that 1 kilo ohm and 200 ohm which are in series, through that I2 is flowing, and the rest of the current, which is 1 milliampere minus I2, that is flowing through the parallel combination of two 2 kilo ohm resistors. Okay, so here also we need to do a lot of things to find out the value of I2. Okay, and now we have to do another step. We are activating only the 1 milliampere source. Okay, and we are just removing this the other 1 milliampere source, and we are shorting the 2 volt source also. So there we can see that if the current I3 is flowing through the 200 ohm resistor, then the rest of the current, which is 1 milliampere minus I3, that is flow through the 1 kilo ohm resistor, which is in parallel with the 1 milliampere current source. Okay, and now you can see that this I3 is flowing through, since there are two parallel combination of 2 kilo ohm, so this I3 will be splitted equally. So it will be I3 by 2 and I3 by 2, and then it will sum up, and then this I3 will again come back to the node. Okay, so here what will happen, that this I3 plus I2 plus I1 is equal to the I, which is given in the question. So to find out I, we have to do a lot of solutions. We have to do a lot of pen and paper work to find out the single I, and it is time consuming. So that is why I have thought that why not we use a source transformation and a bit of Millman's theorem. Okay, so let's do first the source transformation and then apply Millman's theorem into it. We can easily apply Millman's theorem across this two node. Okay, so let's first discuss that what is Millman's theorem, and then we can solve it easily. Here is our Millman's theorem, where we can see that there are n number of voltage sources that are in parallel, and each of the voltage sources has an impedance of R1, R2, R3 and Rn respectively. If we look from the node XY, then if we just deactivate the voltage sources, then we can see that our Thevenin equivalent, or say Norton equivalent resistance R equivalent, is nothing but R1 parallel R2 parallel R3 up to parallel Rn. Okay, and when something is in parallel, then what I do, I generally do the reciprocal of the sum of the transconductances. Here the transconductance is 1 by R1, 1 by R2, 1 by R3 to 1 by Rn. Okay, so here what we are doing, we are just trying to Thevenize this thing, where there will be a open circuit voltage or a Thevenin equivalent voltage, and then there will be an R equivalent. So a Thevenin equivalent voltage in series with R equivalent, that is connected from node X to Y, and then there is a load. Okay, so that is our aim. Or we will have a, say, Norton equivalent short circuit current, which is in parallel with the R equivalent and which is connected with X and Y, and over there another load is connected. So interchanging the voltage source and the current source, or do the source transformation, we can see that a current I1 is flowing because of V1 and R1, because current I1 is equal to V1 by R1, current I2 is equal to V2 by R2, current I3 is equal to V3 by R3. So we can easily replace it with a current source having magnitude of current I1, which is in parallel with its impedance, which is R1. Then there is a current source I2, which has an impedance of R2, which is in parallel, and then it is connected to the node X and Y, and from the node X and Y there is a load which is connected. If we just short circuit the load, then what will be my short circuit current? It will be the sum of all the currents, that is from I1 to IN, that is V1 by R1 plus V2 by R2 plus V3 by R3 and up to Vn by Rn. And we know that the Thevenin equivalent voltage is nothing but Norton short circuit current. Okay, that is multiplied with the R equivalent. Okay, so here my R equivalent is nothing but 1 divided by sum of all the transconductances. Okay, and my current, which is IN, that is V1 by R1 up to, say, Vn by Rn. Okay, so between these two node X and Y, the equivalent impedance is 2 kilo ohm parallel 2 kilo ohm. So it is only 1 kilo ohm. Okay, and what is my current which is flowing? The current which is flowing, that is 2 volt divided by 2 kilo ohm, that is 1 milliampere through one branch. And in the next branch, how much current is flowing? That is flowing equal to again 1 milliampere. So we can actually treat it like a 2 milliampere current that is flowing, and in parallel there is a 1 kilo ohm resistor. Or if we change into the voltage, then what we will get? We will see that there is 2 voltage of source, and that is in series with a 1 kilo ohm resistor, and then there is 1 kilo ohm resistor and 1 volt minus to positive, and then the current I1 is flowing through the 200 ohm resistor. So my I will be equal to 3 voltage divided by 2.2 kilo ohm, because this 2.2 kilo ohm is in series and with a voltage source, added voltage source of 3 volt. Okay, so the I will be equal to 1.36 milliampere, some sort of this. My last topic will be related to an Opamp. op-amps related question, and here you can see that in all the op-amp there is a negative feedback. So anyhow, the nodes, the concept of virtual short or the concept of virtual ground, okay, that is applicable. Okay, so there is no need of going into detail. That virtual short concept is applicable. Okay, so your V plus and your V minus for all the op-amps are equal. If we look into the initial circuits, okay, so then the top circuit is a inverting amplifier because the input is applied to the inverting terminal, and in the below circuit, in the initial stage, then the input is directly connected to the non-inverting terminal. But in every cases we can see that there is a negative feedback where the output is again connected back to the input, and that is to the inverting terminal. So at the top, the output will be equal to V in into minus R2 by R1, and in the bottom amplifier, the output will be V in into 1 plus R2 by R1. I think these are the basics that we know. Now if I just remove the two initial stages circuits, then we are seeing that there are two voltages, V in into minus R2 by R1, and there is another input which is V in into 1 plus R2 by R1, and which both are flowing through R3, and the node V minus, which is at the negative, that is connected at ground. Op-amp is in a negative feedback loop, so naturally the V plus and V minus are equal, so the V minus is equal to 0. Okay, so the current which is flowing through the R3 is actually getting flown out of the R4 and going to the output. So if we calculate, then the current which is flowing through R3, that is given in the left hand side, and the current which is flowing from the zero potential to V out, that is minus V out divided by R4. Then if we calculate the closed loop gain, then it is V out by V in, that is equal to minus R4 by R3. That is my answer. So I am ending over here. So please do subscribe to our channel and do comment if you have any doubts. Thank you everyone, and all the best to everyone. Thank you.